And for my next trick, a complex AI model from nothing. Meet Madison. She's a great person because she wants to help people. That's why she's an Asurian expert. Asurian has many types of experts to providing technical support to their customers. Experts come to people's homes, they work in stores, they give voice support, and they give messaging support. Madison works on the messaging support team by chatting and messaging with her customers. Now, she enjoys what she does, but she has a tough job doing it. You see, because she has to type a lot of messages every single day, again and again, and it's a huge drain. This is not efficient for Madison. Or in corporate speech, this is a pain point. Here's an example of a message that she has to type very often. Now, wouldn't you get tired of typing this message every day, again and again? And here are other types of messages that she keeps on having to retype. Now, this is not just Madison, because in truth, we're dealing with a problem with a much larger scale. You see, at Asurian, you have hundreds of experts, just like Madison, who need to respond to tens of thousands of sessions every single day. Hi, I'm Matityahu Sarafzadeh, and come and see how we used AI to make Madison's life easier. I'm going to share with you our journey with the stumbling blocks met upon the way, while building for Madison a system to help her avoid retyping those same messages again and again. We'll talk about the challenges faced during the data collection process and during the modeling process. And finally, we'll see the solution, which helped us reach our goal, building a high-accuracy, complex model from the little amount of data that we had available. But first, a little bit about myself. Born and raised in Houston, Texas. I moved to Israel in 2010. I've been working in AI since 2015. A year later, I earned my bachelor's degree in telecommunication systems engineering from the Jerusalem College of Technology, Machon Lev. I've been working as a data scientist by Soluto, by Asurian since 2019, and in 2021, I became the data scientist team lead. My job at Soluto is to make Madison's life easier. So one of the gifts that our team gave her was the Can Messages feature, a prepared list of ready messages where she can simply scroll through, select the message that she wants, and send it to the customer, thereby saving Madison much time from retyping that frequent message again and again. But we still had a problem. Because you see, now Madison's Can Message library became very large. In addition to the default list that we provided her, she has her own list of customized and personalized Can messages that she saved herself. So now, instead of helping her, it takes her even longer for her to search for the desired message. So, we decided to use AI to automate and auto-suggest the Can message. And for the first iteration, the focus was on predicting the permission to troubleshoot Can message. Why this message? First of all, it was a product decision. It gives assurance to the customer that the problem will be properly investigated, and also creates a unified language amongst all the experts at Asurian. Here's some messages. For example, can I ask you some troubleshooting questions? Or I need to ask you a few questions to understand your issue. Will that be okay? This is in a stage in the conversation where Madison already speaking to the customer on the in-house built messaging platform. You can go visit the product hub and see a little bit more. And with this in-house client that we built, after she speaks to the customer a little bit and she introduces herself, she needs to probe the problem. So this is the permission to troubleshoot message, where she basically says, I understand that there's an issue. I think I understand the problem. And this is the Can message. Do I have permission to run some troubleshooting? The question was, the Can messages seem basically the same. They are a little bit different. So what is exactly the thing that we want to do here? And that's exactly what we're going to talk about. That's our cold start. The data collection, creating something from our nothing. You see, ideally, as a data scientist, the way I like to prepare data is very simple. Make a query, get a data set of all the chat sessions, those which use the permission to troubleshoot Can message, and maybe some which didn't, to add some noise to the model. Very simply, run a model on it, LSTM or whatever you want, and done. Everyone lives happily ever after. And exactly your question. What happened? Going through the sessions, going through our data, we found very few sessions which use this default permission to troubleshoot can message, because many sessions weren't troubleshooting related. And those which were, not necessarily did Madison prompt the permission to troubleshoot can message, the one that we wanted her to choose. And even when she did, many times she used her own personalized version of the can message. So we want to create a data set. And we don't have much data to predict that can message. We have some few messages here and there, that small variation, that cold start, but we needed more data. So we introduced NLP fuzziness to help us label more data to train a model. Let's talk a little bit more about fuzziness. Fuzziness is the technique of finding strings that match a pattern approximately rather than exactly. For example, you have the word apple. So fuzziness would group the word apple with similar permutations of the word, such as APLE, APPL, and apples. Let's talk a little bit more about fuzziness. There's a famous algorithm in the NLP fuzzy world, the edit distance. Made in 1965, not too long ago. It's used to measure the difference between two strings by counting the minimum amount of single character edits to get from one word to the next. These edits could include inserting a character, deleting a character, or swapping a character with another. Take, for example, we want to find the edit distance between the word kitten and sitting. So the edit distance is 3. Kitten to sitting. If I want to get from kitten to sitting, first I need to swap the K and the S, then the E and the I, and then add to the last letter a G. Edit distance of 3. So let's talk a little bit more about edit distance. Here's another phrase. Hello, how are you? How many characters are there? 18. What about a series of the letter Z? 18 times. How many characters are there? 18. What's the edit distance? 18. But what about this? Hello, how are you? And a nice chunk of text. Now, that same chunk of text without the hello, how are you in the beginning. What's our edit distance over here? Also 18. But are these the same 18 differences that we need? Are these, in other words, comparable? No. And that's why we had to normalize our edit distance. In other words, take our edit distance that we found and divide it by some length, the max length in this case, in order to have all the edit distances compared. So in other words, between two strings, this one and this one, we have an edit distance, but that's still not the final edit distance. We have to normalize it so we can start comparing apples to apples. So there we go. With this edit distance, we devised the fuzzy match hybrid algorithm consisting of the normalized edit distance, regex, regular expressions, perfect match, and manual handpicking. We use this bag of weak, you can say, text algorithms to find other similar messages. And we were able to find more messages, but because we're matching a pattern instead of exactly, we're actually matching a pattern approximately. And unfortunately, it still did not help us get more data because the Seder Godel, the order that we had to get to, was much larger to train a larger data set that we'll see soon. So we used the power of semi-supervised learning. Semi-supervised learning is a method where we combine a small amount of labeled data with a large amount of unlabeled data during the training stage, helping us deal with our problem of a small amount of labeled data. Research has indicated that semi-supervised learning can give considerable results with less the amount of labeled training data compared to a fully supervised learning project. Addressing our problem here, we have a little amount of data, and we wanted to train these larger LSTM models. So you're asking, if we're dealing with the technology of bots and there's data everywhere, why are we missing data? The way our messaging platform works is that everything is done in-house. So we have a messaging platform that we built here at Soluto.
But you don't label the data. You bring it somewhere from India or like...
So we do label the data, and we're going to talk about how we, well, I'll say in a second why. Here, I'm going to throw some chocolate, right? It's here to throw. He asked if we label the data, if we outsource our labeling. It's a very good question. For certain security reasons, we can't do that. Because this data has sometimes not personable information, because then we can't even store it, but sometimes it has information, even though it's not personable, we'd rather keep it in-house and not outsource it due to other security reasons. So good. So you're saying, why not take a conversation that was already happened and work with that? We tried, but we didn't have enough data to train a model. When we'll see the numbers soon, you'll see how much more data we had to get to even train a model. Because this CAN message that we wanted to use was almost never used. You see, these are all the CAN messages that we could have predicted. Product decided to predict the permission to troubleshoot CAN message. But there's also closing, hello, hellos, insurance, dead airs, like hello, are you still there? That had plenty of more data. You can see much more. But the troubleshooting had about, I don't know, it looks like 50 there. In other words, we didn't have enough data. This is that cold start that we're trying to deal with. So we have to make data, or pretend like we're making data, and that's what we'll see. So you're all exactly reaching the same points that we did. We needed data. We didn't have enough, but we needed to train these deeper models, to understand language. So using semi-supervised learning, which is literally the power of creating something from nothing, which we'll see how, we came up with the semi-supervised algorithm. How do we do it? We started with the permission to troubleshoot messages, those few messages that you mentioned, that cold start. Then we calculated the fuzzy match with all the other potential messages. If it passes some match threshold, it was added to that list. Then, when it was scalable at least, we reviewed, verified, and removed anything incorrect. And finally, rinse and repeat. We went back and did it again. And in every single run, we kept growing the pool. So once we got to the bottom, let's say we doubled our list, we just went back up again and ran the algorithm again, and again, and again, and again. But it got more interesting as it went. At first, due to the limited amount of data that we had available, that small amount of data, as you mentioned, we had to use these weaker-based models, the fuzzy match hybrid algorithm. And exactly like your question over there. And again, the output of this model served to be the label for that sample. So we're not predicting messages yet. We're building models to label data for us. But once we're able to obtain enough data, we got to evolve from a Charmander to Charmeleon. We're able to use machine learning models, bag of words, TF-IDF, and LSI. And that's exactly your question. N-grams and all those fun things, you need a little bit more data to do it because you're dealing with the curse of dimensionality. So we need more data to label, but we don't have data. So we have to start weak first, keep growing that pool, and it gets more interesting as it gets bigger. How much more interesting? Once we got even more data, we're able to use LSTMs, transformers, and encoders. Great, we have our data. But remember, in semi-supervised learning, these are only the soft labels. The labels which are generated by the output of an algorithm. If you want to use semi-supervised learning, you also need gold labels. Gold labels are those high-quality, gold labeled data tagged by who? Human beings. But we don't have. That's how we got into this problem in the first place. So we created the session tagger program to generate synthetic data. How? By manually injecting the target message into sessions which didn't use the CAN message, but could have benefited from it if it did. And our results, for the synthetic data generation, we collected a few hundred labels. To remind you, these are those high-quality, hand-labeled data, the gold labels. And for the fuzzy algorithm, we collected about 1,000 labels, labels which are set based on the output of an algorithm, the soft labels. So now we have data, and we move to the modeling process, urging our nothing to learn something. Let's talk about our model's features. We use the sender, the dover. Is it the customer? Is it the expert? Is it another bot that we have as a feature? We use the message number in the session, a meta feature. The number that this message was amongst all the other messages relayed back and forth in the session. The fourth message, the second message. We also encoded the message's text with Google's universal sentence encoder. And we also used the length of a message as another feature. Now you see this was done for every single message in the data set, but also every message had a window of the 10 previous messages leading up to that message. In other words, we had a 3-dimensional data set. X features, N samples, and an L, a lag of 10 messages leading up to that sample. So now we have a model, we have data, we have labels. Now we'll move on to the training stage. So we'll need to choose a proper validation metric to help us. Why do we need a validation metric? Hyperparam tuning, early stopping, selecting the best model. That just names a few. So what about accuracy? What about, we'll see in a second maybe why not. Let's take another example. Here's our typical confusion matrix. This is what the model predicted. This is the true value. And this is the confusion matrix, or as I call the confusing matrix of everything. True positive is when it was actually true, and the model also classified it as true. True negative is the opposite case, where it's not true, and the model also said it's not true. False positive is when the model thinks it's true, but it's really not. False negative is when the model thinks it's not true, but it really is. Let's take a data set where we want a model, to predict a dog versus a cat. In our confusion matrix, we'll see we have a total of 24 photos by adding up all those inner squares. 20 dog photos and 4 cat photos. Let's run accuracy. We have a diverse crowd, so I'm going to run on some things and run less on other things. Running the accuracy, basically doing the true negatives plus the true positive divided by all the other results. We got an accuracy of 79%. How is that? Not so good, because we have a major class imbalance. We have 20 dog photos and 4 cat photos. So let's move on to imbalance metrics. There's precision. What's our precision here? 18 divided by 18 plus 3. It looks at everything that it predicted positive. Precision, 86%. What's wrong with precision? Precision doesn't look at how much of the once class was detected. In other words, if I have a classifier that finds almost nothing or very little, I'm going to get a high precision. So let's move on to recall. Recall does look at how much of the once class was predicted. What's our recall here? 18 divided by 18 plus 2, 90%. Because recall is it calculates the number of true positives that were correctly classified. However, recall doesn't look at those which were predicted correct. It only was able to measure how much of the once class we were successful to join. So what do? The harmonic mean? The F1 score. So 2 times 86 times 90 divided by 86 plus 90, 88%. We have an F1 score for this model of 88%. Is that good? No? Actually not. Why? Take a look again at the matrix, specifically at the classification of the cat photos. We like cats too, right? Only 1 out of the 4 cat photos was successfully detected. Moreover, 2 of the 3 of the photos classified as cats were actually dogs. So we're only able to find correctly 1 of the cats. How do we get such a high F1 score? Because we missed a spot. The F1 looks at the true positive, the false positive, and the false negative. But what about our poor little true negative? It was totally ignored, giving us a high F1 score. If you don't believe me, let's flip it over. Now, the cats are positive, and the dogs are negative. What's your F1 score? 29%. Is that such a good metric? Introducing the MCC score, Matthew's, or because I love it, Matityahu's correlation coefficient. Why is this great? Accuracy is sensitive to the class imbalance. You don't use accuracy when you don't have a balanced data set. Precision, recall, and the F1 score, they are not symmetric. They're asymmetric. So what do? Let's treat the true class and the predicted class as 2 binary variables. And what do? Compute their correlation. running the correlation coefficient between them tells us an indication is what was predicted correlating with the reality with what happened. This is known as the phi coefficient, Pearson's coefficient, the R2 score. These are all cousins. They're all derived from the same basic function of Pearson's coefficient. Why do I love MCC? So we said it's symmetric. And it has great attributes as well. You see, if the FP and the FN are both 0, the value of the MCC is 1. If the true positive and the true negative are 0, the value is a -1, just like our correlation coefficient. What about 0? 0 means you're better off with the random classifier. It's much less work to do, because there's no relation between what I predicted and what the reality was. You see, MCC is beautiful, right? Takes into account all 4 values of the confusion matrix. A high value, close to 1, we're doing great. A low value, not so great. And 0, not at all. So plugging it in, what's our MCC on the cat and dog data set? 0.17. Wasn't such a good metric, right? However, MCC equates a false positive and a false negative. And as much as I love MCC, in our case, it doesn't answer on the product and the business level. You see, at Soluto, we're a product-oriented team. We're a business-oriented team, where it's not enough that we just have good metrics. It has to answer to the product level as well. And that's what we always strive for, to choose those metrics that don't only look good, like an F1 score or maybe complement of F1 score, or maybe joining them together, but something that's able to look at the proper metrics. And the MCC did not look at the true negative metric. So we used something else called the F1/2 score, and we'll explain why in a second. Part of the reason that we'll get into right now was because on a product level, on a business level, precision was more important than recall. Don't worry, I'll explain. When we have something that's a high precision, what does that mean? We have less false positives because the model is doing well in lowering that FP and raising the TPs. And to remind you, positives are when the model actively suggested something. A positive is when the model would say, the next message is that can message I want to predict, shoot. So when it's high, we have a low amount of times where the model predicted too early or too late. It predicted on time. What about recall? On a product level, we're defining these metrics on a product level. A recall is when we have as little as false negative. A high recall is when we have as little as false negatives as possible. Because to remind you again, negatives are when the model decided not to suggest at all. So when the recall is high, that means we have a low amount of times where the model missed the opportunity to predict. So let's join it together. There's the F1 score. The F1 score gives an equal cost. It gives an equal importance to the precision to the recall, or in business terms, to the false positive and to the true and to the false negative. The F1/2 does something a little bit different. It gives a slightly more importance to the precision than it does to the recall. And this is all based on the beta. If the beta is greater than 1, the metric will favor the recall more than the precision. And when it's less than 1, as we said, it favors the precision a little bit more than the recall. And this is much better than just choosing precision over recall, because it's important that the model doesn't miss the opportunities. We want it to look at both. Just one on a business level is a little bit more important. Why is this so important on a product level? Because we prefer the customer's experience, that precision, sending things at the right time, much more than the conversion of the session, the recall, those missed opportunities to potentially save some money. And this is to hold the retention and the happiness of all the users that we have to support. I didn't get into code because of the diverse audience. I don't know if I have a screenshot. We had the features I showed you, which were those meta features and the embedding. So that's like 512, plus like a few other meta features, like 7 or 10. Then we had a lagging onto that. So every message and the window of the previous messages. That rings a big bell of LSTMs and sequence-to-sequence transformers. The data set we're going to talk about in a second. The amount of layers, I'm trying to remember. It was about like 7 layers, some dropouts in the middle. The bigger problem wasn't the complexity. It was fighting the unbalancedness that we'll find right now. So, good question. What was the complexity of the model? But I don't have to repeat the answer, right? You got chocolate, right? So we have our labeled data, we have our model, we have our metric. Let's finally train it, right? So we have our data set. The label of every X of all the features was, is the next message a message that Madison should predict to be the permission to troubleshoot message? How do we do this? It was time series data, because a session is all time series. The expert's talking, he's talking back. The order is very important. So we split into blocking windows with no overlap between the windows, because we just had a lot of data and we didn't have to reuse any of it. Having a lot of data left us with a huge label imbalance, because as we've seen, this message was used at most only once per session, if at all, leaving us with a class ratio of 98 to 2%. And as you probably predicted, the model couldn't converge. So we had to re-engineer the data set by undersampling, moving from a target label ratio of 98 to 2% to 89 to 11%. The undersampling was done to increase the one's presence in the data set and to help the model better learn from it. Now, there are other methods to deal with data imbalance other than unsampling. As a data scientist, I hate it when I'm throwing away data. But being a product-oriented team, sometimes doing what's right is what's wrong. Sometimes just putting the model onto the shelf to literally save the company millions of dollars is what's important. So undersampling did it well, because the model, and how do we know that? Because the model began to converge. You see, the label proportion was imbalanced enough to resemble the reality, that high imbalance that we had naturally, but it was low enough for the model to converge. So we started heading in the right direction, but we still were not optimized fully according to the business. This is because the model's loss function didn't take into account our label imbalance, that standard loss function of the model. It was learning mostly from the 89% of the zeros class. But the ones class is also important to learn from. I would argue, maybe even more important. We just didn't have enough of them in the data set. Why shouldn't the model learn from them equally? Why should it deduce everything from that large other class? They should be equal at least. So we introduced the binary focal loss to help the model better learn from that lesser label. What is a focal loss? Imagine you had a soccer game. Barcelona versus Madrid, in a stadium packed with hundreds of thousands of fans. All of a sudden, there goes Messi. Gets around him, shoots a goal. Goal! 70,000 fans are chanting in the stadium, goal! Now, those at home are able to hear those 3 TV telereporters telecasting the game. But how? Then a stadium with 70,000 fans drowned it out. How could they hear those 3 TV reporters? There's 70,000 fans screaming goal and everything else they scream at after a goal. How can they hear them? Because the sound room implemented a focal loss. It amplified the noise of those 3 TV reporters and decreased the noise of those 70,000 fans. And the same here. The focal loss amplifies the weights learned by that ones class and reduces the weights learned by that zeros class, helping the model better learn from that smaller class in the data set. And the rest was history. The loss converged, the F1 increased, and with early stopping before the overfitting and optimizing the threshold via the PR curve, because it was imbalanced, so we can't use the ROC curve, we have to use the PR curve. We received the final results of the model with F1 micro of 85% and F1 macro of 64%. Even more interesting, something that we strive to do is see how we can improve. So we started analyzing the model's results after the predictions. And we learned that many of the false positives were actually acceptable if they happened in real life. And this got interesting. Like, why were these false positives even acceptable? And we started learning something about the experts. Everyone has a different personality, and we took data from everybody. Sometimes an expert would take a long message and just shoot it. Sometimes the expert would take a long message, split up into smaller messages, and send each one separately. Sometimes even a question mark as his own message. because it's free to send messages, right? So with this high variance, if the model predicted something a little bit earlier, it still would have been acceptable. So our next steps would be using a scoring method to credit those false positives which are still acceptable. In other words, not just an F1/2, but a fixed F1/2, which will go in there and also help us credit those false positives which would have been acceptable. And of course, technology just goes. This project was done about a year and a half ago. Since then, GPT-3 has hit the shelves pretty well. BERTs have been out there, other encoders. We want to try them out. And we want to use all this technology to predict other types of CAN messages as well. So, back to Madison. Next time she's on the messaging session, helping the customer. Thanks, I have one more issue. I have a problem with my home Wi-Fi. And the model predicts she should send the CAN message. She just clicks on it, sends it, helping her job, bringing people closer to the technical devices at Asurian, much easier. The beginning where I show you the distribution of the different CAN messages.
Yeah, where you have distribution of the CAN.
So that was real data. That was real data that we pulled, sitting with the product, helping the product decide what message to predict. So we showed all the different types of CAN messages that existed, and the product decided to predict that one. Now, product people, they're great. Sometimes they don't understand data science. So when they want to predict a troubleshoot CAN message, and it's used very rarely, the answer is, yes, Your Highness, and we just get it done. Yeah, it was a human that did it. So at first we said, let's just go through all the sessions and just pull from the database all the sessions that were done, find those CAN messages that we wanted to predict, find those sessions which used them, and learn from that. But because it was rarely used, we had that cold start, that small amount of messages, where there were some different types of version of the message, and that's why we had to get into fuzziness and to find similar messages and add synthetic messages, all just to add data to the data set to avoid as much as undersampling as we can. The question was, were those messages designed by us to see what we should choose, or was it real data? So it was real data, yeah. You're asking why we care so much about this message if it was in this specific business case. So we spoke about it earlier. We're trying to have our experts have a unified language because it's the same reason why soldiers in the army all wear the same uniform, why people that work for a certain corporation wear the same exact clothing. It adds some sort of uniformity to everything. Why this specific CAN message? So the product really wanted those troubleshooting messages to be dealt with. And we took this project in iterations. So we always try to get the model onto a shelf and build the next thing. And that's how we always kept building it. Like every time we did an iteration, as you saw that we kept growing the pool, that immediately went into a model and was put on shelf, no matter what the accuracy was. Because we try to get on the shelf as fast as possible. Now, this CAN message was the most simple CAN message to do some fuzzy matching with. Because the other ones were much longer, like a guide of how to reset your Wi-Fi. It's very long. Go into settings, click on the kebab, those 3 buttons, and et cetera, et cetera. So this was one of the easier permission to troubleshoot messages to start with. And once we got the framework built to help us fuzzy label our own data without outsourcing it just due to other reasons, this helped us build that infrastructure. Yeah, that's a good question. You're asking, do we, as a product level, get feedback on the performance of our models? We do. In almost every single product that we're putting out, we monitor it live, seeing, after we launch it to make sure everything's good. And afterwards as well, we always want to make sure that the model is relevant. We get alerts. We see when things are not going well. And just even today, a model that we had in production, it was already being reconsidered. Is it time to retrain it, or should we do some other things to it? But we're always checking for that data drifting. And we're always making sure that our test and validation set resembles the current reality that we have now. To make sure, because if in the validation set we did pretty fine with 64% and 85% micro-macro of F1/2, we want to make sure the reality is still the same. So we do, time to time, sample the data, making sure we don't have a data drift, use algorithms to measure data drift. Good question. That's a very good question. You're asking, how do we know when to start? How do we know when to stop doing the iterations? So what happened was, we had a hard deadline for this project. So we said and in machine learning, there's always 2 different debates. Should we should we invest our time in labeling data and having a good quality data? Or should we invest our time in training the model and, just doing the magic there? So based on just a lot of research that exists, it's always learned that more data is better for a model compared to better algorithms and more complex algorithms. So our goal was always to try to get as much data as possible. Now, at the same time, we had a trade-off. We had to get this on shelf as fast as possible. So our strategy was for us to always make our deadline, as long as the model on shelf was fine enough. What we kept doing was build the model, going through that iteration, putting it on shelf. And as long as we still had time to our deadline, we just kept going. When it finally came to a level that the product said, this is a good enough of a result, we stopped. But until then, our strategy, doing the semi-supervised iterative approach, we were always able to have something ready on the shelf. So we would never, by accident or even intentionally, spend too much time labeling data, but I don't have enough time to train it. Or I'm spending too much time training, I could have labeled more. It was always balanced, because we always spent time labeling the data, then we spent 2 days training it, putting it on shelf, another 2 days labeling, and then it just kept going for weeks, and I think a few months.
Make sure the examples that are coming in are not too fuzzy. And
Yeah. It eventually comes to a point that we start data drifting, and all the data starts, not data drifting, that we become biased with the data. That our data always becomes, kind of similar permutations to what was before, and that's why we have to generate synthetic data. So sometimes we would send other types of messages, and we would team up with product to try to see if we could get other types, just to add diversity to the data set, and inherently it would also go in fuzzy from that and learn from that. So that's a good question. I can't answer too much about that, but what I could answer is that the use of canned messages has increased. The question was, how much did this affect the usage of the canned messages? This whole effort raised the awareness of the experts using the canned message. Part of the reason to automate the canned messages was that the experts were going in there and they were just typing these messages, and even though they had some mini version of a canned message library, they just didn't use it. And our goal was that you don't have to use it. Let's just find what you like to use and just help you use what you like to use yourself. So it did raise awareness to the experts in the canned messages, and it did increase the usage of the canned messages as well, and the message suggestions only can add to that. So that's a good question. That was the plan. The plan was that putting this in production would give us more data for the next stages. But with these results, as long as there's no data drift, there's no reason to invest on a product level on this message. Let's go into the more complex messages. And probing these messages engages the use of other canned messages as well, and we can start predicting those now. So this is why you have to be very connected to the product and to the business, because it really affects it. What hardware? We try to develop as much as we can in the cloud, just because it's there. It follows you everywhere you go. AWS, that's what we like to use. SageMaker, Jupyter's. This model was an LSTM model. As I said, with about 7 layers, some good amount of dropouts, the customized loss that we spoke about. But it's time to move to GPT. It's time to move to transformers, fine-tuning. These are all the next steps to these projects. You're asking, do we have some method to detect other popular messages that are used and predict those? That's basically what you're asking? So that's a very good question. There is a model that our parallel data science team in Nashville, Soluto is owned by, I didn't speak about it much in the beginning, I can speak about it now. Soluto is owned by Asurion. Asurion is a company in America that provides tech care to the customers, helping people with pretty much any device that has a power button, washing machines, telephones, your computer. So over there, there's a data science team as well that we work in parallel with our team here in Tel Aviv. They developed a model that goes through the whole session and summarizes the session, because sometimes an expert wants to follow up on a session. So instead of saying, oh, tell me what your problem was, and the user's like, I just told you 25 minutes ago, scroll up. So it takes time for the user to write that. That also lowers the customer satisfaction. It also takes time for the expert to scroll up. So we do have a model on that, summarizing a whole session into an actual paragraph of, this is what the expert said, this is what the user said, that's the conclusion, everyone had a nice day, or didn't. There wasn't a product need for what you said, but there is another similar product need for what you said, which we also developed it as well, is to find those hot messages that are usually used by the expert, by other types of product hacks that we did and other features that we did that inherently raised the usage of the canned messages. and helped us, the data science team, know what are the more appropriate messages that we should predict today, and on those we predicted. So you're kind of asking like, a message came in, it's that type of message. Those two products exist, but there was no product need to join them together. Good question, though. Here. I'm a lefty. Nice. Anyone else? Thank you so much for coming. This was great. Thank you for sticking back. Have a good night.